a piece of string. It could be any length. Let's just call it length L. And then you're going to have a certain amount of it, let's say length X, and you're going to cut it and make a square out of that much. And then you're going to use the rest, let's say orange here, the rest of this, which is L minus X, and you're going to make a circle. And then obviously the circle gets smaller or larger as X changes. So we're going to let L represent the lengths of the string, and then the cut and the remaining is L minus X. So each side of the square is going to be X over 4. So the area of the square is X over 4 squared. Now when you have the circumference of a circle, right? The circumference of the circle is L minus X, and the circumference of a circle in general is 2 pi r. So solving for r, we have that the radius of the circle is L minus X over 2 pi. So the area of the circle is pi r squared. So we're going to take pi times this r squared. And let me make this bigger here. When we simplify it, we get L minus X squared over 2 pi. Okay, so the goal of this, going back to here, is that we want to imagine maximizing both the area of the square and the area of the circle. So we want to add those two areas up, and that's our function, okay? So here is the area of X. It's equal to the area of the square plus the area of the circle. So the first thing we want to do when we're trying to maximize is take a look at the derivative. So we take a derivative here. This is going to be 2 times x plus x over 16 to the 1. And then here we have 2 times pi times L minus X to the 1 times, don't forget the derivative of what's inside. The derivative of that is negative 1 over 4 pi squared. So doing a little bit of cancellation here, we have 1/8 x. If you're multiplying by negative 1, I can make that x minus L and cancel out the 2 and make that a 2, and the pi cancels, and you're left with x minus L plus 2 pi. Okay, so now we have our derivative. We usually want to set it equal to 0, so we want to figure out. So hopefully this is some function that has a maximum at somewhere within this interval. So we can find somewhere for the length of this x to be equal, to be the largest area. Well, interestingly, we note that this is actually a line, right? Because each of the powers of x is 1. So what we're going to do, though, is we're going to set the derivative equal to 0 and solve for where this line crosses the x-axis, right? What value of x causes that to be 0. So we set that equal to 0 and do a little bit of math here and get a common denominator, and we end up then, so we have 1/8 x times x minus L over 2 pi, get a common denominator here, and then notice that these two have an x in it, so then we're going to move this to the other side, and you're going to factor out an x. So you have 1/8 plus 1 over 2 pi times x is equal to L over 2 pi. Then, solving for x, you're just going to multiply by the reciprocal of this, so you're going to have L over 2 pi times, getting a common denominator here, of 16 pi, you have 16 pi divided by 2 pi plus 8. If you want me to do that step out, what we're saying here is that we want to add these two things up since they're both constants. So the common denominator would be, actually it would probably be 8 pi, but I use 16 pi. So 1/8 is equal to what over 16 pi? That's times 2 pi, so that's 2 pi over 16. And then 1 over 2 pi is equal to what over 16 pi? You're going to multiply by 8. So we have 2 pi plus, this right here is 2 pi plus 8. So I could rewrite this as x times, x times 2 pi plus 8 divided by 16 pi. And that's going to be equal to L over 2 pi. Now, when I want to multiply by the reciprocal of this to both sides. So that's where this comes from. That's the reciprocal. So we end up with L to be this value here. Excuse me, X to be that value there for any L, which is kind of cool because the point is that this answer would be the same regardless of what L that you use. So I decided to do it the generalist way we could. Well, now we want to do is to check to make sure that this value is a maximum. So we can, one way to determine if something is a max or a min is to take the second derivative. So when you look at the first derivative, if I take the derivative of the first derivative, I get the second derivative. And what you notice here is you're going to get 1/8 x, and this is going to become 1 over 2 pi. Because this is it's just going to be, again, if we take it out, right, we have x over 2 pi minus L over 2 pi. So that's 1 over 2 pi, and then this is just a constant. So the derivative of a constant is 0. And we end up with an equation, or excuse me, an expression that has no powers of x in it, which means it's a constant. So that if the second derivative is a constant, it's always going to be positive, right? And again, we knew this because the derivative is a line, right? So a line only has one slope, and it has a positive slope. So what that tells us is that the function is concave up because it's always positive. It's a parabola that's concave up all the time, which means that this critical point must be a minimum rather than a maximum. But remember, the question said we want to find a maximum. So it's going to look something like that. And the lowest point is what we just found. So now we need to check the endpoints because we want to find a local, right? So again, going back to our diagram, what would be the endpoints? Well, get back to green here, right? If I move x all the way to the end here, so x is 0, and we just have the whole line being L, that would be 1, and so that would be when x is equal to 0. And the other possibility would be when we move it all the way over here when x is equal to L. So those are our two endpoints. So when we plug in x equals 0 in the original function, we get 0 over 16 plus pi times L minus 0 over 4 pi squared. So that becomes L squared over 4 pi. And so that is really cool because what we're saying here is that it doesn't matter what L is, right? But when you make only a box, right? When you're only making a circle, that's the area of the circle. That means, right, you're only making a circle. So remember that the area of a circle is pi r squared. And so if L is the line, again, we have L is equal to the circumference, which is 2 pi r, which means that r is equal to the circumference, which is L, divided by 2 pi. So we have the area is going to be equal to pi times r squared, which was L over 2 pi squared. So we end up with L squared over 4 pi. Just wanted to check that to show you how cool that is, that it does make sense, that it does work. At the other end, if we put L in, well, that's when you have only boxes, which is L squared over 16. So here's our two choices. We have L squared over 4 pi or L squared over 16. Since 4 pi is like 4 times 3, that's going to be a little bit smaller than L squared over 16, right? And if a fraction has a smaller denominator and the same numerator, that means it's going to be greater. So that means that the circle, when you have no cut at all, is bigger than the endpoint when you only have a square. So therefore, the largest area occurs when the wire is used to make a circle rather than when the entire wire is used to make a square. So hopefully this makes sense intuitively, because we know that a circle with circumference L has a larger area than a square with perimeter L.